Alrighty, so year 10 we've looked at how to create linear functions in mathematics. So obviously I'll upload that video so you can have a look. But now we're looking at some of the more advanced features of Google Sheets. It's much the same as what we've done before. But what we're going to be looking at is a few different types of graphs. Now I've created these functions so they perfectly match. When you collect data, it won't perfectly match. So just going to get that elephant out of the room straight up. What we're going to look at here today is some of the types of functions you can model and what you're sort of looking for, and what we can do as far as using Google Sheets as a powerful tool. So the first thing I'm going to do is I'm just going to select my data. I'm going to insert a chart, and I'm going to see how that looks. Again, the line chart's no good to us. What we want is a scatter plot. Scatter plots are our friend. Time is the independent variable there, and I'll just try and blow this up a little bit. Time is the independent variable there, and a dependent variable is distance. Okay, we can see by looking at that graph straight away that's not a linear function. Okay, there's a clear upward trend in the curve. Okay, so we've got a trend, but it's not linear. So let's try and find out what type of trend we've got. So we go back down exactly like we did before. We click trend line. Okay, and we can see straight up. I'm just going to increase the thickness of that line, make it 70, make it a 4-point line, and I'll change the color so we can see it very clearly. Let's make it red. Okay, we can see very clearly that's not the graph that we want. That's not a model that effectively finds our data. We can click our R-squared value to prove that. It says 0.93. Okay, so that's okay, but it's not the best R-squared value. We can clearly see that that's not a very good function for our data. So rather than going for a linear, so up here where it says linear on the right hand side, rather than clicking linear, what I want us to do is instead we're going to pick polynomial. Okay, now polynomial, and it says polynomial order 2. What that tells me is that it is a quadratic. Okay, it's a quadratic, which means that it's of the form something x squared. Okay. As we can see, that matches our function pretty well perfectly, and if we look at our r-squared value up here, we can see that it does in fact hit our r-squared value is 1, so we can see that it perfectly matches our function. Again, I'm going to use my equation up here, and this has got some pretty gross words, and I wouldn't mind zooming in on that. How do I zoom in on that? Let's try and... I want to make this as big as possible. Okay, up the top here you'll see we've got negative 1.94e negative 16 plus 1.44e negative 16 x plus 0.16x squared. Anytime you see e, what that means is times 10 to the power of. When I read that, 10 to the power of negative 16 is a tiny number. So you've got negative 1.94 times 10 to the negative 16. That is no good to us. Okay, that's way too small, so we ignore that. The function is really y, which is distance, equals 0.16 times x, which is time, squared. What I've done is I've created a falling object with an acceleration of 0.16, so we'd expect, 0.32. So we would expect to see our function is quadratic. Are we clear? That's an example of a quadratic. I expect that's gone over a few of our heads, so that's fine. What I wanted you to take out of that was, firstly, we can do other things apart from just a straight line. We can use other functions. This was a polynomial order 2. Okay, really good. We use that when we've got data that looks like it's curved and it's on the way up. Now you could set polynomial order 3 potentially, but more often than not, if you're picking a polynomial of anything other than an order 2 or negative 1, then you're probably in the wrong spot, or negative 2. But we'll talk about that later. What we're going to do now is look at a different type of function, time versus speed. We'll see what type of function we get here. Actually, we'll come back to that. We'll do time versus speed below. This is a function I want us to look at. We're going to insert a graph. Let's get used to doing this. Scatter chart. Now we can see this has got a curve. I wouldn't mind if this extended a little bit higher, but it starts up at 100 and works its way down in a pretty odd looking pattern. So again, I don't exactly know what it is, but I've got a pretty good idea that it's not linear. I've got a pretty good idea that it's not like the one that we just saw before. Okay, I want a nice thick red line. So rather than making it linear, I want to go to polynomial, and this time I wonder if I can go -1. No, that won't work. So I can't go polynomial. I want to go power series. Power series must be the one that I want. I'll go to power series, r squared. That's not what I want. I want use the equation. Ah, perfect. Use the equation. Now I don't know. I'll try and make this bigger again. If you look above my function here, if you look above my function, I can see here I've got 100 x to the -1, and what that means is it's 100 divided by x. That is called an inverse function. And what that means is as the function goes along, it gets smaller and smaller and smaller as time progresses. 100 divided by x. So as x gets bigger and bigger, our value should get smaller. Again, this is the sort of trend you will see pretty frequently in physics. And anytime you see that sort of skate ramp shape, that's when you're the half pipe shape, that's when you're starting to think you've got an inverse function. Just a reminder how we do that. So we go to data series, speed. So I'll get rid of my trend line. So I go down, click trend line, click use equation, that's good, sorry, click power series, and x to the -1 means 1 divided by x. Okay, we should know that from our index laws in mathematics, but just in case you didn't, that's how that one works. So that's pretty cool. We can get all sorts of functions, and as you go through and as time progresses, you'll get more familiar with that and you'll get better with that. I know we're just learning, and I know it's a bit to take on. The best advice is practice, and I'll send these data sheets out for you later on to have a look at. Okay, I might fix that one up. The next data set I want us to look at is one that's nice and steady, and I might actually just throw a curveball in here and make this one 1.68. Okay, so I'm going to get my data. I'm going to insert a chart. Now before I say anything, I want you to try and think about what type of function do you think best models that data? What type of function have we got? Have we got a quadratic? Have we got an inverse? Have we got something different? Well, let's have a look. I'm not exactly sure. Let's have a look. I'm going to insert a trend line. Oh, it comes up with linear, 70%. I want that red. Okay, so we've got a linear function, obviously with my outlier that I just threw in there. So if I put my r squared value in, you can see that it's not quite 1, but it's pretty close to. The reason I'm getting this one up is because I want to show you a new feature. Okay, I want to show you, and it's something that we need to do. It's a very physics-specific skill. Okay, and that feature is error bars. Now, if you can't see what I've just put up, those error bars are these little top and bottoms on each one of those functions. Over here it's got a percentage. You can put a percentage, constant, or no error bars. Right now it's operating at 10%. So you'll notice that as you go further along, the error bars get bigger and bigger because 10% of whatever the y value is gets bigger and bigger as time progresses. Now error bars are really important. Okay, you need to be able to use error bars to talk about whether an outlier is reasonable or not. So as we look at this data here, and I'd love to make this I'm trying. As we look at this data here, we can see that this function here, the 1.68, the one that I'm circling right now, well, the one that I'm circling right now with my mouse, its error bar falls a little bit outside the trend line, which means that given the uncertainty or the amount of uncertainty we've applied, that 1.68, that is an outlier. That data should not be included, or we should be explaining why that's occurred. It's really important that you can represent this so you can see whether your data is appropriate or not as far as its uncertainty or in your uncertainty calculations. Now, if I want to change from a percentage error bar, so let's say I don't want to use a percentage because I haven't found a percentage or the percentages aren't quite right, I can change it to a constant value. Now, right now my error bars have got 10, which is way too big, but let's say I had a constant value of 0.05, okay? That's an error bar of 0.05 on both sides, above and below the line, which encompasses my data. I can also add horizontal ones, but at this stage I'm just happy for us to do a vertical error bar. I hope that makes sense. I'll just run through very quickly what I wanted you to take out of this little lesson. Okay, so firstly, we use trend lines all the time to talk about what's going on with the data, what type of relationship we're seeing. Okay, with these we can get polynomials of order 2, which is a quadratic. So that's when you see your data smiling or going the other way. So when it's smiling or frowning, when it's going up on a curve or down on a curve, could be a polynomial. Okay, we've got the linear, obviously. We've got an inverse function which looks like this. Okay, and to make an inverse function, to get an inverse function, we go series. We click on our trend line. Okay, type power series. Okay, to find the function, we look at the top. Anytime we see a negative power, that means we've got something over. So 100 divided by x is what we've got there. That's what 100x to the negative 1 means. So it's 100 divided by x. The r squared value tells us how close our function goes to our data. Okay, so an r squared value near 1 means you've got really good data. You've really you found a trend line that suits your data perfectly. The last thing I showed you was how to do error bars, which I'll just remind us again. If we go down to series, just above trend line, we see error bars. Now we can use percentage, we can use a constant or a percentage is my advice. So if you were to use a constant, you could set a value of 0.05 or whatever you've calculated. And if you were to use a percentage, it might be something like 5%. Okay. Percentage error bars will increase in size as your data gets bigger. Constant error bars will stay the same size the whole way through. You need to calculate your error, your uncertainty beforehand, and then place that data in. Okay, so that is set by you. You don't just randomly, willy-nilly throw a value up. You need to think about, you need to calculate your uncertainty and use that as a way to inform your error bars. Hope that helps. Any issues, please let me know.